We're going to discuss exponential decay and exponential growth. Um, what is a decay? Decay, usually exponential decay, models by a function such as a of t equal to c to the power rt. T is the time, r is the rate that we find, and c is the constant. Halftime makes sense for exponential decay. Halftime is the time that the amount becomes half of the original. Please notice, if I plug in 0 for t, and a of 0 is going to be c times e to the power 0, which is 1. So the original amount is this. And what this is saying is that half-life is when original amount becomes one half of the original amount. The amount becomes one half of the original amount. So one half of c, and then plug in the half-life, and you get c e to the power rt, t half, t sub h. And so solving for t sub h, first of all, we simplify the c, then take the ln of both sides, and we divide by r to get t sub h is equal to ln of 1/2 divided by r. Exponential growth, interestingly, follows the same model, except r is bigger than 0. So in some text, you don't see exponential decay as e to the power rt. You see it as e to the power negative rt when r is positive. But nevertheless, it's the same concept. If I put negative rt with r positive, it's negative r is a negative value that multiplies t. So what multiplies t is always negative for decay. For growth, what multiplies t is always positive. Let's do one example of a calculation of things and how we deal with the algebra of things before doing an exponential decay problem. So let's start with a of t model, a of t be equal to c e to the power rt. Some information is given to you, and you always need that information. Usually from a word problem, you want to extract information such as this. This one is telling you that a at time t time 10 is equal to 20. This one is telling you that a at time 0 is equal to 4. A little bit more clear here, 0 equal to 4. And so we are going to use that to find c, r, a at time 20, and t such that a of t is equal to 100. So what do I know? A of 0 is equal to 4, so I plug in again a of 0, although we've done it over there, equal to 4. Plugging in here gives me c e to the power 0. That means that c is equal to 4 because this part is equal to 1. We found c. Now let's find r. The other piece of information that I have is a of 10 is equal to 20. A of 10 is equal to 20. Plug it into the, now I have c is equal to 4, so I plug it into 4 e to the power r times 20. The only variable is r. I simplified this side to get 5, this side 1. So I get e to the power 5 equal to e to the power 20r. Take the ln of both sides, divide by 20, and you get r is equal to ln of 5, natural log of 5 divided by 20. So we found both of them. Now I can write the model the way it should be. A of t is equal to c is equal to 4, and then r is equal to ln of natural log of 5 divided by 20 times t. The next step is to find a of 20. How do we find a of 20? By plugging in 20 inside this function. So ln of 5 divided by 20 times times 20. In this case, 20's simplify together, and we get what we end up with is 4 e to the power ln of 5. E to the power ln, these two are inverse function of each other, and we end up with a 5. So 4 times 5 equal to 20. And so that's the final answer. So a of 20 is equal to 20. And then a of t, we have to calculate a of t. Oh, we have to calculate time t such that a of t is 100. Plug in t on the other side of the equation right here. And we get 4 e to the power ln of 5 divided by 20 times t equal to 100. Simplify to solve for t, and that would be e to the power ln of 5 t divided by 20 is equal to 25. ln of both sides, and we get t is equal to natural log of 25 times 20 divided by natural log of 5. That's one answer. That's another answer. And the model looks like that. C are the model a of 20 and t such that a of t is equal to 100. We're discussing exponential decay and growth, and usually this entails some board problems. First, let's talk about the model. Exponential decay follows a of t equal to c to the power rt when r is less than 0. When we're talking about exponential decay, often we talk about half-life. Half-life is the time that amount becomes half the original amount. Let me talk about original amount. Original amount means the amount at time 0. So a of 0, if I plug in here, I get c times e to the power 0, which is 1. So a of 0 is always this, the amount at t equal to 0. And so now, if I set the other side, if I plug in the other side of the equation with the half time, that would be c e to the power rt sub h, then the output should be 1/2 of a c. And if I solve this, I get c simplifies from both sides, and then I will have 1/2 equal to e to the power rt sub h. Take the ln of both sides, ln of 1/2 is equal to ln of e, which simplifies because they are inverse function, r times t sub h. So t sub h is ln of 1/2 divided by r. Now, exponential growth, it has the same model. So when you see exponential growth, you also see a of t equal to c to the power rt. The only difference is, in here, what multiplies t is positive. In here, in the decay, what multiplies t is negative. Sometimes, to be more clear, people write down for decay c e to the power negative rt when r is positive. Again, negative r would be negative, and what multiplies t is negative. Now let's do an example. Let's say A of t is equal to c to the power rt is the model. And a bunch of information is given. Let's say a of 10 is equal to 2, a of 0 is equal to 4, and then can we find c, r, a at 20, and t such that a of t is equal to 100. First, since I have a of 0 equal to 4, I can replace it right here, and I get 4. So C is easy to find again. A of 0 is equal to 4, therefore C is equal to 4. The next thing, can I use this piece of information? Yes, I can plug in 10 in the model, and the output should be 20. So 20, and I know C, that's 4, e to the power 10 times r. Now solve for r by, first of all, by dividing by 4 to get 5, and then taking the ln of natural log of both sides, 10r, and r is going to be ln of 5 divided by 10 equal to r. Let's rewrite the model. Now that I have r and c, I'm writing a of t is equal to 4 e to the power ln of 5 divided by t times t. Okay. The next thing to do is use this piece of information to find a of 20, because now I have a model. I can plug in 20 and get something out of it. So a at 20 is equal to 4 e to the power ln of 5 divided by 10 times 20. So this is going to be equal to 4 e to the power 2 ln of 5. I can simplify this because this is e to the power ln of 5 to power 2. This part is 5. 4 times 5 to power 2, which is 100. Now, the last part of this question is asking, find t such that a of t is equal to 100. Now, at this moment, I actually know the time t that makes the output 100. That's 20. So t is equal to 20. That's when output is 100. And that time is 20. But if I didn't know, and I was not lucky enough to solve for a of 20, I would not have known, and that's the answer. So I should have solved for t such that a of t is equal to 100. How do we do that? Let's go back over here. What we need to do is, in the model, plug in that t. So 4 e to the power ln of natural log of 5 divided by 10 times t, and set that equal to the output, 100. And then we have to solve for t in here. So this is the t time, and I'm using capital letter because this is specific t. So e to the power natural log of 5 divided by 10 times t is equal to 25. Take the natural log of both sides, and you get ln of 5 divided by t times t is equal to natural log of 25. You can simplify this. Ln of 25 is actually ln of 5 to power 2, and therefore it's 2 times ln of 5. Simplify this, and you will get that t over 10 is equal to 2. Therefore, t is equal to 20, which is the same answer that we already had. Next, I'm going to do one exponential decay, one carbon 14 decay problem up on the board. So in exponential decay problem, let's say half life of carbon 14 is 5,730 years. First of all, write an exponential model for the decay. Then find if 20% of the carbon decay has already decayed, of carbon 14 has already decayed, what is the age of the artifact? Over here, I gave you a formula. If you know the decay, the rate of the decay, you can figure out what the half-life is. In here, the half-life is given, and you want to find the rate of the decay. How do we go about this? When you're writing a model, you usually write A of t, amount at t, is equal to c to e to the power rt. Now, half-life means if I plug it in, I get 1/2 of c equal to c e to the power rt half. Now, if I simplify, do the same thing that I did over there, and this time solve for r, I'm going to get r is equal to natural log of 1/2 divided by half-life. That is natural log of 2, negative of that, because natural log of 1/2 is natural log of 1 minus natural log of 2, according to the properties, divided by 5,730. Now, for a model, we only know r. I don't know what the amount is. All I need to know, original amount is, all I need to know is the percentage that decay is happening. So I'm going to write A of t equal to c to power, that's the r, times t. Okay, so this is the model, part A. Now, part B is asking, use that model to estimate the age of an artifact. Please notice that it says 20% decays. That means 80% is remaining. So for A of t, which is the output, putting point A, C, then equal to c e to the power negative ln of 2 divided by 5,730. And we're trying to find time, so I'm going to put in capital letter T, as in there's a specific time that this is happening. Now, to solve this, the first step is we figured out 0.8 is equal to e to the power negative ln of 2 divided by 5,730 t. Take the log, natural log of both sides, and you get natural log of 0.8 is equal to negative natural log of 2 divided by 5,730 times t. Now solve for t, and that would be 5,730 natural log of 0.8 divided by negative natural log of 2. This is going to end up to be a positive value. You can use your calculator. The reason is that ln of 0.8, which is less than 1, is going to be a negative value, and simplify by negative ln of 2. I leave this to you to find out what time it is and how old the artifact is using your calculator.